Cartesian coordinates in 3D. So let's go ahead and draw up an X, Y, Z axis. So Y-axis going across, our X-axis here, and Z-axis here. And we're going to mark in the points A being 1, -1, 3, B is 2, -4, 5, and C is 5, -13, and 11. So we have our X coordinate of 1, Y coordinate -1, and Z coordinate as 3. Should get us about there for point A. B at 2, -4, and 5. So that's going to get us about there for B, and C at 5, -13, and 11. Which might get us somewhere about here. Now, we want to show that these points are collinear, which means that we should be able to draw a straight line between all three of these points. We want to show that it is possible to draw a straight line between all three of these points. Now, one way to do it would be to show that the distance of AB plus the distance of BC would equal the distance of AC. And if that worked out, that would mean the points are definitely collinear. So let's go ahead and get expressions for all of those distances, just using the distance formula. So we can use distance formula in 3 dimensions. So first, let's go ahead and do AB. So this will be the square root of x2 minus x1. So we use point B's coordinates for x2, so it'll be 2 minus 1 all squared plus -4 minus -1, so +1 squared, plus z2 minus z1, so we'll get 5 minus 3 squared. And if we simplify all this, we'll get root 14. Let's look at BC now. So we get BC as the square root of, we'll use C as the second point. So we'll get 5 minus 2 all squared plus -13 minus -4, so +4 all squared, plus 11 minus 5 all squared. And simplifying this will give us 3 root 14. And finally, let's look at AC. So we'll get the square root of, let's use point C as the second point. So we'll have 5 minus 1 all squared plus -13 minus -1, so it'll be +1 all squared plus 11 minus 3 all squared. And if we simplify this, we'd get 4 root 14. And we can see that if you add root 14 and 3 root 14, we will get 4 root 14. So we can conclude that these points must be collinear. We could also do this with vectors though. So that's what we're going to have a look at now. We could look at the vector of A to B and then look at the vector from B to C. And if we're able to express one of these vectors as a scalar product of the other, it will mean that the vectors are parallel, and we can also show that if they share a common point, they must also be collinear. So we're going to go ahead and find expressions for the vector AB, A to B, and expressions for the vector B to C. So we can get an expression for the vector AB by doing the vector from O to B minus the vector from O to A, and B to C, we can do O to C minus O to B. So let's go ahead and look at vector AB first. So vector O to B, we can just use our coordinates and express it as a vector with its I, j, and k vectors. So the vector O to B is just going to be 2i minus 4j plus 5k, so that's just using the x, y, and z coordinates, minus vector OA, which will be I minus j plus 3k. And if we simplify this, we'll have 2i minus I, which is I, minus 4j minus minus j, so it'll be minus 4j plus j, which is minus 3j, and 5k minus 3k is 2k. So that's what we get for our vector from A to B. Let's look at our vector from B to C. So it's going to be our vector O to C, which is just going to be 5i minus 13j plus 11k, minus the vector from O to B, which we've already found, is 2i minus 4j plus 5k. And doing this subtraction, we're going to get 5i minus 2i, which is 3i, minus 13j minus minus 4j is going to give us minus 9j, and 11k minus 5k is going to give us 6k. And here we can factorize out of 3. So when we do that, we're left with I minus 3j plus 2k. And I minus 3j plus 2k is just the vector AB. So now we can express BC as 3 multiplied by the vector AB. And this successfully shows that these two vectors are collinear, as they both share point B and they're parallel to each other. Another thing when we look at Cartesian coordinates in 3 dimensions is, let's draw up our XYZ axis. So our x-axis, our y-axis, and our z-axis. And we want to look, if we have a point with coordinates x0, y0, and z0, and we want to look at some point P with coordinates x, y, z, where that point is always a fixed distance away from that starting point of R. So we're looking for all the points that describe a distance of R away from our original starting point. We'll call it O. So let's draw in a few. So we get R, R, and this is in 3 dimensions. And maybe you can see that this would actually describe a sphere. centered around that point O. So we'd have a sphere, it'd be the surface of a sphere. So this is in 3 dimensions. And how can we express that? So we could say that the distance of P to O is always fixed. So we could say PO is just going to be the square root of x2 minus x1. So we'll use the point x as our second point, minus x0 all squared plus y minus y0 all squared plus z minus z0 all squared. And we know that distance PO is equal to r. And we'll square both sides. So then we'll get r squared equals x minus x0 all squared plus y minus y0 all squared plus z minus z0 all squared. And this will actually describe the equation of a sphere. You might see it in the form where r squared just equals x minus h all squared plus y minus k all squared plus z minus l all squared. And in this case, the radius of the sphere would equal r, and the center would be at h, k, l. So let's have a look at an example question. We want to find the radius and center of the sphere described by this equation of x squared minus 2x plus y squared plus 4y plus z squared minus 8z plus 5 equals 0. So we can recognize that it's a sphere straight away by saying that we have an x squared component, y squared and z squared, and all of their coefficients are the same. They all have a coefficient of 1. And to put the equation of the sphere in this form here, we need to do a triple complete the square. So that's what we're going to do. So we're going to start off by just making a little bit of space after our x, y, and z terms and take our constant to the other side. So we're going to have x squared minus 2x, and we'll leave a space, plus y squared plus 4y, leave a space, plus z squared minus 8z, leave a space, and take the constant to the other side to get minus 5. Now we need to add 3 terms to each side of the equation that will help us complete the square. So on this side, we're going to half the coefficient of x and get minus 1 and square it. Here we'll add in half the coefficient of y, which is 2, and square it. And here we're going to add in half the coefficient of z, which is minus 4, and square it. So minus 1 squared is 1, so we need to add it to this side. 2 squared is 4, so we also need to add it to this side. And minus 4 all squared is 16, so we need to add it to this side. Now we can successfully complete the square. So for all our x terms, we just get x minus 1 all squared. For our y terms, we get y plus 2 all squared. And our z terms, we get z minus 4 all squared. And then minus 5 plus 1 plus 4 plus 16 is just 16. And now we've got our correct form of the equation of a sphere, where we can easily say the radius is going to be the square root of 16, which is equal to 4. And it's going to be centered at the point 1, minus 2, and 4. Let's look at one more example. We're going to look at 2 equations of spheres. One at x minus 1 all squared plus y squared plus z squared equals 16. And x minus 5 all squared plus y squared plus z squared equals 49. And the first thing we're after is we're after the value of x when the spheres intersect. So after the value of x when the spheres intersect. So let's draw a bit of a diagram to see what's going on. Might be a bit difficult to draw, but we'll give it a go. So we'll have our x-axis and our y-axis and our z-axis. Now, let's draw in this first sphere. So it's going to be centered at 1, 0, 0 with a radius of 4. So we'll draw the sphere in blue. So it's going to be centered at 1, 0, 0, so this point here, 1, 0, 0, 0. And it's going to have a radius of 4. So it's going to extend to this point 1. So if it has a radius of 4, it's going to extend over here to minus 3 and out here to the point 5. And we're going to get something like this. For this sphere here. Now the other sphere we'll draw in red, and that's going to be centered at the point 5, 0, 0 with a radius of 7. So we might extend our x-axis a bit. And so it's going to be centered at this point 5, 0, 0, and it's going to have a radius of 7. So it's going to go all the way out here to minus 2. And it's going to come all the way out here to 12. And we're going to get something like this. For this sphere here, where it's centered around this point here at 5, 0, 0. Now it's kind of difficult to see, but what's going to happen is these spheres are going to intersect with each other, and they're going to intersect in a vertical looking circle shape, somewhere about there. And by solving these equations simultaneously, we're going to get a bit more information in what's going on. So in order to get this curve of intersection, we need to solve these simultaneously. So let's call this one equation 1 and this one equation 2. And we're going to do equation 2 minus equation 1. So we're going to get 5 minus x minus 5 all squared minus x minus 1 all squared. Then the y squared minus y squared will be 0. Z squared minus z squared will be 0. And then 49 minus 16 on the right hand side is going to give us 33. We can just go ahead and expand the left-hand side. So we're going to get x squared minus 10x plus 25 minus, let's expand this next bracket, we're going to get x squared minus 2x plus 1 equals 33. We're going to have x squared minus x squared, so they'll cancel out. We're going to have minus 10x minus 2x, so we're going to have minus 8x. Then we're going to have 25 minus 1, which is 24, and all this equals 33. Well, minus 24 from both sides, so we're going to get 9. 33 minus 24. Divide both sides by negative 8, so we get x equals 9 minus 9 over 8. And what that tells us is that when x equals minus 9 over 28, minus 9 over 8, somewhere about here, that will be the center of this intersecting circle. But we can go ahead and find the equation of that circle by just subbing in this value to x into either one of these equations. So let's go ahead and do that. So we'll sub it into equation 1. So we'll get minus 9 over 8 minus 1 all squared plus y squared plus z squared equals 16. This is going to be minus 17 over 8 all squared plus y squared plus z squared equals 16. This is going to be 289 over 64 plus y squared plus z squared equals 16. Subtract the 289 over 64 from both sides, so we're going to get y squared plus z squared equals 735 over 64. And this is the equation of the circle of intersection for these two spheres. And it will have a coordinate. Well, there's no x term, so the x coordinate of the center is 0. The x coordinate of the center we know is minus 9 over 8. And its y coordinate is 0, and its z coordinate is also 0, and it has a radius of root 735 over 64, which simplifies to 7 root 15 over 8, which is about 3.4. And this hopefully makes sense that the equation of the circle is y squared plus z squared, because it's parallel to the zy plane. So normally we're used to seeing circles parallel to the xy plane, where they're in the form x squared plus y squared equals r squared. But if we have an equation of a circle parallel to the yz plane, it has to be in the form y squared plus z squared.